Hello, this is our second episode on the standard model with Professor Ananthanarayan from the Indian Institute of Science, Bangalore. If you haven't watched the first episode yet, you should watch that one first before you watch this one. Professor Ananthanarayan is professor at the Center for High Energy Physics at the Indian Institute of Science, Bangalore, where he has also served as head of the department and guided several PhD students, including at least one of my own former colleagues. He did his BTech at the Indian Institute of Technology, Madras. Switching to physics, he then earned a master's in science and a PhD in physics from the University of Delaware in the US. Anant is a member of the editorial board of the European Physical Journal A and the Indian Journal of Pure and Applied Physics. His research interests are in the field of elementary particle physics and quantum field theory. He works both at the frontiers of the standard model and high precision, and also at finding signatures of interactions that lie beyond the standard model, that is, at finding new physics that can be uncovered at the International Linear Collider. He has also worked on dispersion relations, on the chiral symmetry of the strong interactions, and on grand unified theories and supersymmetric models. Anant is a prolific writer, a popular speaker, and a recipient of the Homi Bhabha Fellowship and the Rustam Choksi Award for Excellence in Science. With that, it gives me great pleasure to invite Professor Ananthanarayan to join us.
Welcome back, Professor Ananthanarayan. In the last episode, we ended by discussing renormalization, and let me just ask you to explain why it's called renormalization and what do you mean by renormalization group?
Yes. So I was trying to explain to you that if you go to the next to leading order in perturbation theory, then you start seeing the appearance of such things as these loops, where it is essentially like producing an intermediate state where the momentum can be distributed between, say, two of the particles in this case. And there's nothing to say what their individual values are, except that their sum has to be equal to the incoming energy momentum. There's overall energy momentum conservation. And we said that there has to be a sum over all intermediate states, as we saw in the quantum mechanical case.
Okay, you seem to have frozen out there.
It will not be a denumerable set, but a non-denumerable set of intermediate states where there's a continuous variable, which is the momenta carried by this. So this infinite sum that we had in the case of quantum mechanics is replaced by an integral. After all, you will remember from your high school calculus that an integral is obtained as a limit of a sum. For instance, let us say you look at the integrated rainfall, say in 1 year, is the area under the curve. That's the integral. It's like you can replace that integral by a bunch of histograms, and then you sum over all those histograms. And in the limit that the width of each of those histograms goes to 0, then you get a continuous distribution and an integral. So similarly, just like the sum over intermediate states is now replaced by an actual integral. And these each of these momenta can run all the way from 0 to infinity, the various individual components, subject to overall energy momentum conservation. So you might suspect that this thing may lead to something that may diverge, even though it is divided by these denominators, which is analogous to the energy denominator that we had on the first slide. You have this energy denominator. So you may think that this particular representation of these intermediate states sum is a sum over all these continuous variables divided by various denominators, and this thing may not actually may not converge. So then there is a whole problem associated with the rise of such divergent integrals. But then this program of renormalization allows you to account for these divergences and to reabsorb these divergences into a redefinition of the parameters of the theory. It sounds like black magic, but it actually works because it goes into what is meant by an observable theory, that is, in the absence of interactions, anyway, you would not be able to see anything. And the
That's what.
parameters of such a theory, of a free theory, would be almost impossible to say what it means unless there are interactions. And this interaction between interactions and these infinities leads to this program of renormalization, which appears counterintuitive, but there are intermediate steps where all these quantities are made sensible. They are what is known as regularized, and then the infinities are controlled, and there's the reabsorption of such infinite quantities into definitions of the theory. So, does that somehow answer the question that you had?
Yes. And I think that's what Schwinger, Tomonaga, Feynman, and all got their
Yes,
Nobel Prize for, right?
Exactly. And it's not as if these effects are not observable. For instance, if you have a free particle like this and it emits and reabsorbs a photon, you may say, hey, what's the big deal? Anyway, it's a free particle and it's not observable. But such a thing, actually, there is an observable effect, for instance, in a hydrogen atom, where you compare an electron that is sitting inside one of the orbitals of hydrogen atom compared to that electron being liberated and being free. So that difference actually becomes an observable quantity, and that is what is known as a Lamb shift. There are two contributions to the Lamb shift, one which comes from the self energy, another from this vacuum polarization. This thing was known as the Ewing term, which was already kind of known before Lamb's work. And this Lamb shift is a splitting in one of the hydrogen atom lines. It's a very, very interesting and important thing. And when
And
it
this
was
has been
experimentally reported,
experimentally observed to very high accuracy, right?
yes, that's right. Yeah, but this was already observed in the 40s by Willis Lamb, and when this was reported, Hans Bethe, actually at a conference, he on his way back home to Cornell University, which is in upstate New York, I guess from Albany, where this conference took place, he's supposed to have estimated this Lamb shift, which is about 1080 megahertz. He estimated it using it literally a back of the envelope calculation in that whatever journey. So it just shows the kind of control that these people had on all the numbers and the facts and so on, and the insight, and the profound insight. So this is as far as these two basic diagrams are concerned. One of the observable effects is this Lamb shift, whereas this other one, which is called the vertex correction, which is responsible for what is known as the anomalous magnetic moment. Now, this Dirac theory that I had already mentioned at the classical level, which is just tree diagrams like this, predicts a value of G equals 2 for fermions like the electron and the muon. So any departure from the value of 2 is represented by G minus 2 and often divided by 2, G minus 2 by 2. It's called the anomalous magnetic moment. So this is also an observable effect, and it was computed by Schwinger, and he got the answer of alpha by 2 pi, where alpha is 1 by 137. And this was observed by Polycarp, Kupsch, and Foley around the same time as the Lamb shift, and then this was a Nobel Prize which was shared by Lamb and Kupsch. So it's not as if these effects are just bookkeeping and trying to make sense of the theory. They have observable effects.
And recently there was some recent measurements of the G minus 2 for the muon, right?
That's right. That's at very high precision, G minus 2 of the muon. It turns out that measurements of the muon G minus 2 are actually somehow easier for a variety of reasons. That would be a separate talk. And I've given several talks on the muon G minus 2 about the experimental principle. The first experiments were done long ago. Then there was a high precision one at Brookhaven National Laboratory, not far from where you did your PhD. And then the magnet that was used there was transported to Fermi Laboratory and then retooled and remachined, and better detectors were added, and then a lot of control on the uncertainties, and they have a new measurement which has improved the accuracy by a factor of 4. And then there is still some tension between theory and experiment, which is what experts are still discussing. So this is all great stuff that is going on. Just to complete the picture, I just wanted to show a few more diagrams at leading order without any loops. For instance, this is what is known as Compton scattering. It's very famous. This shows that is established that, just as you had mentioned, the wave-particle duality for the photon, similarly, the wave-particle duality, both descriptions are needed for the electron, and this was done by Compton very early on, where you have a photon that scatters off a photon that scatters off an electron and re-emits another photon and another electron, and then this cross-section is measured, and this proved the hypothesis that the electron shows both kinds of behavior.
Right. It was
Another famous
one of the early experiments confirming the nature of the electron.
Exactly.
We discussed that in one of our early episodes.
Wonderful. Yeah. Exactly. And then another very famous process is named after Homi Bhabha. See, this was at a time when people were just beginning to grapple with what the Dirac equation meant, what is meant by particle, what is meant by an anti-particle, things like this. So Bhabha, who at that time, soon after the Dirac equation, was a student of Dirac himself at Cambridge, he studied the scattering of electrons on positrons. It so happens that you can have an electron and positron touching each other and producing a virtual photon, and then that turning back into an E plus E minus pair. Alternatively, it is also possible that there is a Coulomb scattering of an electron from a positron given by the second diagram. So quantum mechanically, when there are two contributions coming for any given initial state and final state, then you have to add the two amplitudes and then square it to get the suitable matrix element, and then multiply it by the phase space factors to get the differential and integral cross sections. Now, all this seems very obvious now, but we are talking about the early days when things were just, the subject was just in its infancy. Then there's Moeller scattering, which is electron scattering off another electron, just Coulomb repulsion. So this is field theory, that is, electron 1 scatters from the field set up by electron 2. So this is in contrast to, let's say, Rutherford scattering, which I talked about earlier, where you have, a static electric field that is set up by a nucleus, and an electron scatters from that, or an alpha particle scatters from that. So Moeller scattering is both the particles are relativistic, and each is scattering in the field of the other. So there's another interesting process that was considered very early on, which is called Delbruck scattering, which is light on light scattering. This turns out to be a finite diagram, and Delbruck, soon after this, he moved to biology and then proved to be one of the very influential figures in biology later on. So I'd already mentioned the idea that, these diagrams over here, for instance, the electric charge may get shielded or may be screened because of the production of virtual particle pairs. And today we know that it's not just electron-positron pairs. You can have mu plus mu minus pairs. You can have the tau lepton, which is another heavier cousin, quarks. All these things contribute to the screening of the electric charge. And this was studied very early on, and it was established within the framework of renormalization. Change of the effective coupling constant, that is a very energetic photon that comes in, will probe the bare charge of the electron better than, let's say, a very soft photon that comes to hit it. So this is just some kind of a heuristic way of looking as to why there must be a momentum dependence on why a charge that is probed by an external photon can change. That is, very, very energetic photon just penetrates this, this virtual cloud of E plus E minus pairs that is protecting the charge of the electron. So such a thing is not just a story. It is can be made mathematically rigorous, and order by order there are, in the number of pairs you produce, the number of virtual pairs, the kind of structure of the kinds of pair production and the screening can be studied order by order in perturbation theory. And the mathematical function that controls this kind of flow of these is what is known as the beta function. This beta function itself can be expressed as a power series in the coupling constant. It's all now very well-known science. It's a good 7 decades old, going back to the work of Stückelberg and Petermann. and Gelman and Lowe, Bogolyubov and Shipov, and many other authors. And this is in the context of QED, and later it had to be extended also to the non-abelian wage theories, the Young. Okay, so here we are. We'll share. So in order to complete, I should say a little bit more about typical weak interaction processes also, and what makes them weak. So as I said, the neutron decay, where the free neutron has a lifetime of about 880 seconds. It decays through the weak interaction. Later, I'll draw some diagrams also to show you the quark level picture at which these decays take place. Other decays of interest are, for instance, the decay of radioactive carbon. Radioactive carbon 14C is constantly replenished in nature because of the interactions of cosmic rays with nuclei of atmospheric nitrogen and oxygen and so on. I don't know the exact process, but when carbon is so produced, it is absorbed by living beings such as plants, trees, etc. And so that's the reason why you can date wood using the abundance of 14 carbon on the usual radioactive law. And another important radioactive isotope is 131 iodine, which is a medical isotope, because iodine gets concentrated in the thyroid and can be used in treatment of disorders of the thyroid. So these are all typical weak interaction processes. The sun, for instance, is constantly producing neutrinos, enormous number of neutrinos, because in the various processes that power the sun, we know the various cycles.
Oh dear.
Turning into heat. There's a carbon cycle and so on. Production of heavy nuclei, whereas heavier ones are produced in supernovae. But constantly, because many of these interactions are weak interactions, so there is a corresponding production of neutrinos. It's an entire subject, the study of neutrinos produced in the sun. Experimentally, it's also been searched for many, many decades. Even though it's such a copious producer, it's still a huge experimental challenge to detect them
Because they interact weakly with other matter, right? So you were talking about the neutrinos being a challenge to detect.
Yes, that's
And
right.
I presume that's because they don't interact via electromagnetic forces and
That's right.
they
Their cross
interact weakly
sections
with other
are
matter.
extremely small,
Mhm.
and a keen student should actually try to compare the numbers and check what the cross sections are for, let's say, for the capture of let us say there's a neutrinos on an argon nucleus, which is the basis of some of the experiments, and what is the production rate for radioactive chlorine from these argon nuclei, or maybe it's the other way around, I can't remember. Yeah, it's a capture on chlorine to produce argon activeness, which is one of the principles of the so-called Davis experiment, to see how many such nuclei are produced in how many weeks and so on. So there'll be a product of the number of uh, chlorine atoms that are present multiplied by the cross section will give you the event rate, and how Davis actually did this measurement. It was such a remarkable experiment. That's why he was awarded the Nobel Prize for that. So each of these things that we talk about as part of common knowledge has required participation of large teams of professional scientists over very long periods. Some of them conducted experiments for decades, So there is no Instagram approach to science. There's no Snapchat. It's a lot of perseverance and having a goal and trying to pursue it. Anyway, let me leave aside that for now and just try to continue. Here is another diagram, for instance. I'd already mentioned that pions and kaons. It turns out that in the quark picture, pions and kaons are made up of quark anti-quark pairs, which I represent by this hooked line over here. So that, for instance, a pion decays into a muon and a neutrino through the emission of this virtual W boson, produces a lepton pair. Strong decays, on the other hand, I had already mentioned, for instance, it's possible to have three quarks line up and to give this delta resonance, which is a spin 3/2 counterpart of the proton. But this thing here is so unstable. And when you line up the three spins, it means that there's a large amount of chromomagnetic energy, where quantum chromodynamics is the name of the strong interaction physics. It also has its own electric and magnetic fields or analogs thereof. And this chromomagnetic energy it costs a lot of energy. But if you produce a delta resonance in some collision experiment, which is a spin 3/2 state, then it kind of decays as soon as possible by producing a proton, and the excess energy, this chromomagnetic energy, shows up in the production of pions, because pions don't have any conserved number associated with them. So in a strong interaction, such a thing. So it would be good to compare the lifetime of a pion with the lifetime of a delta, with the lifetime of a pi zero, which goes through something as an anomaly. And there's also the role of this phase space. For instance, the neutron and the decay and the muon decay essentially go through a weak interaction diagram, a simple weak interaction diagram. But why are their lifetimes so different? One of them is about 880 seconds, while the other one is 2.2 microseconds. The reason is that the neutron and proton mass difference is very small. It's only about 1.2 MeV or so. Whereas here, this muon here is very, very heavy compared to the electron and the neutrinos. So on the right-hand side here, you have virtually massless particles, whereas here, there's very little energy that can be distributed between the proton and the electron and the neutrino. So it inhibits the decay of the neutron, the so-called phase space, and that's why the lifetime is very large here compared to the lifetime. So, it's an interplay of all these things.
So could you, on a layman's level, would you understand that in terms of the energy time uncertainty?
No, I don't think so. I think it is just to be understood in terms of this extra energy that the neutron has in terms of the mass splitting between that and the proton, that it's so small that for it to distribute that very little, energy between three recipients is very inefficient compared to a muon that kind of immediately breaks up, like that. So you may think that, supposing you have a firecracker, it's just going to spontaneously explode, it'll just do it very fast. But if the firecracker essentially has to retain its integrity and, emit a few small particles somehow and keeping their integrity. After all, proton, neutron are very much alike. Somehow that extra energy has to be dissipated. Then it's very inefficient. And because it's inefficient, it lives for a very long time.
So that extra energy is manifested as kinetic energy then?
Of these outgoing particles. And the mass. After all, the electron is not totally massless on that scale.
But the difference in the mass.
Yes. The difference in the mass is very small. That's the reason why it is so long-lived. For instance, there are heavy nuclei which never decay, because although there are neutrons sitting inside, energetically it is not possible for these nuclei to decay. So that's why when you go rather high up in the periodic table, only then you start to see radioactive decay, because the Coulomb, the repulsion is quite large, and the attractive forces are not enough.
Right.
And then this large
rather low down when you're talking about the periodic table.
Yes.
Yeah.
For instance, most of these radioactive nuclei eventually end up as lead, because lead is a very strongly bound nucleus. So there is a mass deficit between radioactive nuclei and lead, which is maximum. So there's a maximum energy gap between the radioactive nucleus and the corresponding lead nucleus is the largest. So in the descent, it can also have multiple decays and eventually end up as lead, because it's the most stable nucleus. Higher up in the periodic table. Iron and nickel and all these things are also very stable. So anyway, I just wanted to say that, in weak interaction physics, all these processes are there. And basically today we are studying particle physics at many laboratories with controlled experiments with beams of electrons and positrons, or you can have a large hadron collider. We have proton and proton colliders. And then all kinds of processes take place, and we probe the weak interaction. The weak interaction can be probed at the laboratory level with nuclei, can also be probed at colliders, can also play a role in cosmic ray physics. So it's a very important process, and it's the only process that really allows you to change the particle type. The electromagnetic interactions do not change the particle type, the net particle type. You may say E plus E minus goes into mu plus mu minus, but that's not the point. You never have a complete change in the type of particle as a muon turning into an electron and the neutrino and the nu. Okay. So that's the distinction that I'm trying to make. So these are the preliminaries, and now I think we are here for the mains, and let us see how far we can go. So if I have your leave, I will continue with that, or would you like to stop here and see if there are any questions, or we continue?
No, go ahead, please.
Yeah. So as I said, the idea of this discussion is to present what I would consider as the essentials of the standard model. What is it that physicists, professional physicists understand when they are talking to one another and say that, look, this is the standard model. Standard model of what? In what way is it standard? And what was the need for a standard model? To people like Sukumar and me, the standard, of course, meant a car in the 1970s. But today, the standard model here, this means that there were other competing models also to explain these interactions. And over the years, as many models got ruled out, and the last remaining model, which survived experimental constraints and experimental tests of validation, verification, and falsification, the one that survived is what has come to be known as the standard model. A very prosaic name, and this was a name which apparently was given by Abraham Pais and Sam Treman in some conference talk that they gave. Probably Stephen Weinberg was one of the founders of the subject, also had the same name around that time. And it is a standard model of certain interactions, the names of which I've already mentioned, the electromagnetic, the weak, and the strong interactions. And it purports to describe elementary particles and their mutual interactions due to the force carriers associated with each of these forces is a force carrier. Not only that, these force carriers also, in the case of the weak and strong interactions, have mutual interactions. So they also interact amongst each other. Not only that, there's an extra sector which had to be introduced in order to understand why the weak interactions effectively become manifest only at the subnuclear scale. For instance, in the examples that I gave of neutron decay and of radioactive nuclei, it means that the length scale at which the weak interactions are playing a role is at the subnuclear scale. Whereas the electromagnetic interactions are at a totally different scale, atomic scale, orders and orders of magnitude larger. The Bohr radius, if you think of as setting the scale of electromagnetic interaction, let us say in the hydrogen atom, you compare that to the subnuclear scale, then you will see that there are several orders of magnitude different. So what makes this weak interaction so short range? And the answer is not that it's weak per se. That remember that weak interaction is only a name. The coupling constants or the analogues of the electric charge are still the same, but it's because the force carrier that is called W or Z are extremely massive on the scale that we are looking at. Again, we need to set a scale. We can't say something is large or small. What is meant by big? So we need to calibrate the scale. Every scale needs to be calibrated. So the basic unit we will look at is something like the proton mass, which we already came across in the neutron decay. So you have to remember the number 938 MeV divided by C squared. Now, MeV is an energy divided by C squared. Of course, you can convert it into kilograms and so on, but then when you're talking about elementary particles, that hardly is useful.
For Americans, you can even convert it into pounds.
That's right, yeah. But I think for this purposes of this talk, we'll stick to what is called MeV for mega electron volts, MeV divided by C squared, because energy divided by c squared is a mass. But often we put c equal to 1 in what is known as natural units. And therefore, if I don't mention the c, please assume that it's in natural units. So on that scale, the W is 83 GeV, G as in giga electron volts. So it is much, it's about 80 times as heavy as the proton. And that's the reason why the weak interaction is so weak. Okay? And as I said, in order to make these bosons,
which one is 80 times the mass of the proton?
W. The W. The Z naught is a bit heavier at about 91 GeV.
Okay.
Yeah. The photon, of course, is massless, so we don't have to worry about that. And the gluon is also massless, although it behaves in a completely different way. The strong interactions being so nonlinear and the self-coupling is so strong that you never see a free gluon in life. So nobody has ever seen. It becomes what is known as confined. Although it is massless, it is confined, whereas this photon is massless. I mean, we see photons emitted from the sun, which reach us, photons from the cosmic microwave background radiation. They still reach us, which means that, that they are massless and they can propagate forever and ever and ever unless they are absorbed by something in between. So in order to make this...
And to talk about something which I have not mentioned and probably will not in this talk, what about the graviton? Is that massless too?
Graviton is somewhere. Here it is.
Okay.
Somewhere. A. Einstein, something like that I mentioned. But we will not talk about that here because at the energies that we are concerned with, nobody has seen gravitons, first of all. And anyway, to date, there's no consistent, quantum mechanical theory of the gravitational interactions. What we know about gravity is that it's perfectly consistent as a classical theory, whether it is in black hole mergers or whether it is in, planetary motion and so on.
But can we say anything about its mass and spin?
It has to be because it's associated with a spin-2 field. We have to say that it has a spin of 2 units, Planck units, and it is massless because by construction, the gravitational field, the excitations of the gravitational field have to be massless, and they are extremely weakly interacting, and they have never been observed. Gravitational waves have been observed, but no graviton has been observed because there's no first of all, how do you produce gravitons? Probably you can produce it in the collision of some, celestial objects, and you need a detector that's sufficiently close to the site of the collision and sufficiently sensitive in order to.
Please.
So as we were saying, it is so weakly interacting that even if we have, a detector, there's no man-made detector which is sufficiently sensitive as to be able to measure gravitons and to count number of gravitons and so on. So for most purposes of this talk, there'll be no mention of gravitational field, except that without gravity, the LHC would not stay on the Earth and it would just fly off. And
neither would we.
My time host and I would also be flying off into space. So its role is to keep us all together. Yeah. So just the last couple of words. In order to get a consistent Yang-Mills theory with particles that have masses, that is a W and Z, for them to be massive, doesn't matter what the mass is. It could be 1 MeV, it could be 80 GeV, doesn't matter. As long as it has to be a non-zero mass, there has to be another sector of this theory which involves spin zero particles. Now remember that all the fermions that we mentioned, like electrons, neutrinos, quarks, they're all spin half fermions, whereas all the force carriers, believe it or not, they have to be bosons and they have to be spin 1 particles, with the exception of the graviton. It has to do with the way in which Yang-Mills theories are constructed. Maxwell is a special case of Yang-Mills also. So there's another sector which we call the spin zero Higgs sector, which has to be added to the theory. So it turns out that in the standard model, there's one more particle which gets left behind after all these particles have been given their mass. and that's known as the Higgs boson, whose existence was predicted in 1964, not necessarily for the electroweak model, but in principle it had been predicted. But it took 50 years to build an accelerator and detectors to actually detect it, because its mass was so high that none of the previous machines could have reached that energy to have produced it and to have detected it. So already, as mentioned earlier today, when we are talking about relativistic field theory, which is a marriage of quantum mechanics as well um, as the special theory of relativity, which is due to Einstein, of course, we know that, and quantum mechanics due to Planck and Heisenberg and so on. So, what are the forces? As I said, this is electricity and magnetism, which human beings know from the time of antiquity. It was only much later, let's say about the 18th century or so, that people began to, or even 19th century, saw that they were related to one another. So we had the Ampere's law, and then we had the Faraday's law. Faraday, which said that if you have a magnetic flux that changes with time, then that gives rise to an electric field. And today, all these things are the basis of generation of energy. Let us say at a hydroelectric plant. So that's Faraday's law, and we also know Gauss's law, and so on. So these are all brought together and united in a framework that today we call electromagnetism and goes under the name of Maxwell theory. But then it turned out that electromagnetism does not stand on its own feet, but it needs to be unified with everything that I talked about with the weak interactions. Otherwise, the theory doesn't hang together. And this was put together by these gentlemen, Glashow, Weinberg, and Salam. And it is an extended Yang-Mills theory based on a certain symmetry that we call SU2 cross U1. Why SU2? I'll tell you about these things. And finally, there are the strong interactions due to Fritsch, Gell-Mann, and Leutwiler. Many others contributed to this. But these are the authors to whom it's like attributed as the one place where everything was somehow put together. And all these things, they have the amazing property that they are renormalizable in the sense that I already explained for quantum electrodynamics. This property that, even if you have infinities and all these things, that you can reabsorb the infinities into a redefinition of the parameters of the parent theory without having to introduce more and more and more parameters as you go higher up in this loop expansion or higher up in the perturbative series expansion is a very fundamental property. Otherwise, the theory loses all predictivity. If at each stage you have to introduce a new parameter, it will not make any sense. It can make sense. Sometimes we have to do it when we don't have a choice when we are studying effective field theories. But a fundamental theory, which has to be a candidate to explain these, had better be a renormalizable field theory. Despite the fact that you have a larger symmetry like the Yang-Mills theory, not only do you have a Yang-Mills theory, but you also have this phenomenon of the Higgs phenomenon, where some of these force carriers become massive. I mean, it sounds very crazy, but despite all these things, the theory remains renormalizable. And this was a work of 't Hooft and Veltman, who showed that all these marvelous properties survive despite all these, all these acrobatics that you have to do to make it phenomenologically viable. We are not doing all this just for fun, for the heck of it, or to amuse ourselves. Of course, in the process, if it amuses us, that's fine. But we want to actually make sure that we are explaining the phenomena of the weak interactions, the electromagnetic, as well as the strong interactions. And these, the name under which it goes, where it has these symmetries, so-called gauge theories. Maxwell is a gauge theory, as well as this. So let me explain this notion of gauge theory, which was first given by Hermann Weyl. So a very simple idea, which you had already seen in this Lagrangian that you saw over here. For the moment, you forget that these are, are Dirac spinors. Just think of this as a complex field, and this is another complex field, okay? And forget about turning this off. So you just have a psi bar and you have a d mu and a psi. So that means that if you rotate this psi, which is a complex number, by a complex factor e to the I alpha, then this being the complex conjugate will change by e to the minus alpha. So this psi bar and this psi over here, those two, that rotation cancels each other, provided that alpha is constant, so that this derivative here doesn't do anything to that e to the I alpha. So there is a manifest symmetry present in this Lagrangian that I have written with a psi bar, d mu psi. Okay, there's also a gamma mu for the moment. Okay, is this clear?
Yeah, it's the same thing with the very first equation also, the Hamiltonian.
Exactly.
Yeah.
Yes, right. So this thing over here has a symmetry. So this e to the I alpha, and if alpha is a continuous number, means that there is a set of continuous transformations that leaves us Lagrangian invariant. And that is the primary notion of having a symmetry. Now, supposing this is a more complicated object with components, then you could have a complicated rotation among those, for instance. Okay? Supposing this was a two-component object and this was a corresponding transpose of a two-component object, then you could rotate it, let us say, by unitary transformations that mix up these two components amongst themselves. So this thing over here would have a corresponding transpose of that unitary matrix. And if the unit u dagger u, the unitary matrix multiplied by its transpose, complex conjugate transpose, will just give you unity. That's what is meant by a unitary matrix. So that 2 by 2 matrices, set of 2 by 2 matrices, gives you a symmetry associated with such a thing. Okay, so that's the origin of symmetries of Lagrangians. Now, if you take this e to the I alpha that I had mentioned over here, and not just mentioned, but I have written down over here, if you promote this e to the I to something that depends on space-time x over here, then the d mu is going to start producing derivatives, and then the Lagrangian will no longer be invariant. From the chain rule of calculus, the derivative, when it hits this, will produce a derivative of alpha of x. Now you may say, then what am I going to do? What happened to that symmetry? Or is there no symmetry and like the whole thing collapses? The answer is the next step, where this a mu that you introduce, you require it to transform in exactly that way so that that additional term is cancelled. So this is the beautiful notion of a gauge field, which has exactly the opposite way of transforming as the derivative here coming from the chain rule. Okay, and when a gauge field has the required transformation law, it is known as a gauge field. Now, all this sounds like mathematical tricks, but suffice it to say that these things were done by these authors over a long period of experimentation. They tried this, then they tried that, and then they found the correct principle in order for that to be done. This is how the notion of gauge invariance arises and the gauge field arises, and this is something that is quite important. And for electromagnetism, is the simplest kind of gauge field, because for electromagnetism, the gauge symmetry is a very simple rotation by a complex number. And for more complicated theories like SU2 Yang-Mills, you may have multi-component objects and you may have rotations among those using unitary matrices. So if you have a more complicated rotation, then you may need a larger number of gauge fields in order to compensate for that complicated set of derivatives that arises. And in fact, it will turn out that the number of generators of such a gauge group is going to be equal to the number of gauge bosons that you need with the correct kind of transformation law in order to cancel that additional term that comes from the chain rule of differentiation of calculus. Okay, so that is Yang-Mills theory and Maxwell theory made simple in about 5 minutes. So that said, the electroweak theory, which I said, is what today we accept as a theory of the standard model. Unlike electromagnetism, which needed only one gauge group, it requires a larger gauge group because it has an SU2 cross U1 theory. And SU2 has 3 gauge bosons, and the other U1 has 1 gauge boson. So together you have two W's, W plus and a W minus, you can identify them by their electric charge. That's a nice thing. You can use the same electromagnetic field and give the quantum numbers under electromagnetism to distinguish between them. There's a W plus and a W minus, and then there's a Z naught and a gamma. Actually, the Z naught and gamma are born in the SU2 cross U1. There's one combination of these which is called W3 that sits with W plus and W minus, and the other one is called B. And there's this W naught and the B combine in such a way so that one combination gives you the Z naught and another combination gives you the photon. This photon remains massless, whereas these three guys become massive, not necessarily with the same mass. These two have to be the same because they are particle and antiparticle, but this Z naught is different and is somewhat heavier. So as I said, the space of 2 by 2 unimodular matrices is what makes up this unitary group, and it's called SU2. And you'll recall that this SU2 is also the algebra of rotations, and its generators are the so-called Pauli matrices. It's interesting, in the same mathematical objects that show up in non-relativistic quantum mechanics equips you to do a lot of this. Of course, the contextual meaning is different, but it's the same mathematical object. So that's not enough. These three guys have become massive, while this thing has remained massless. So what to do about that? So historically speaking, this SU2 cross U1 symmetry was proposed by Glashow as the symmetry of the electroweak interactions. Probably already by Schwinger, who was his advisor. But he didn't know how to get it into this form of getting two W's and a Z and a photon. The idea of breaking this down properly and arranging it in a proper way is what goes under the name of the Weinberg-Salam model, that you have to, is a term that's used, spontaneously break the symmetry into a residual symmetry that is called electromagnetism. And in order to do that, you have to introduce this extra sector that I already mentioned, which is the Higgs sector of the theory. And in doing so, we produce these particles with masses that had to be measured. It was actually predicted by the theory. And in 1984 in CERN, these particles were produced, and now we have a ton of statistics on their properties, and a lot of things are known about them. But it took another 30 years for the last remaining prediction of this model, which is that there should be one surviving Higgs particle. In fact, what is required is that 4 Higgs fields had to be introduced in order to do this, but 3 of them disappeared in the process of making the W and Z massive, and one lone Higgs was left, which finally was discovered in the year 2012. So you see, the standard model is such a peculiar thing. You have one part of it that remains very familiar, namely the Coulomb phase and infinite range force, one photon. There's another which is like totally counterintuitive, and this is called the Higgs phase, where part of these symmetries are spontaneously broken. And then there is this other sector of the strong interactions where the quarks and gluons are forever trapped inside ions and neutrons and so on. It's called the confining theory. It's not very surprising because today we know this quantum chromodynamics, which is a Yang-Mills theory with a lot of self-interactions and so on, has the exact opposite property as electromagnetism. We mentioned the renormalization group evolution. We mentioned that the coupling constant of electrodynamics grows as a function of energy because of the screening of the charge. It turns out that some of these Yang-Mills theories without too much matter are actually anti-screening. It's totally amazing. So this means that at large energies, the theory behaves almost as if it's quasi-free, that the forces between the quarks actually decreases as a function of the momentum transfer. So such a property is known as asymptotic freedom, which explains why at low energies it becomes very strong, and at high energies it becomes quasi-free. So the weak interaction is somewhere in between, whereas for quantum chromodynamics it is most dramatic. And this theory here is based on a larger theory, even larger symmetry, where you had here the rotations among 2x2 matrices. Here it's among 3x3 matrices, which are also unitary, and S stands for the fact that the determinant of these matrices is equal to 1. Without the S, it would be U3, in which case the determinant of these matrices could be any complex number whose modulus is 1. Now, this also took a lot of work to figure out that this is the correct symmetry. So just as here the SU2 needed 3 generators, the SU3 here requires 8 generators, and these are called the Gelman matrices, which he had introduced in a different context in the 1960s. He had introduced probably in the late 50s. And the strong interactions of the quantum chromodynamics is a theory of interactions of these 8 gluon fields among so-called colored quarks. Now this color is only a name. He gave this name color because there are three types of quarks, and because they also have to white out amongst themselves, he was motivated by the idea of having 3 primary colors. It has nothing to do with the color that our eyes see. It's just a name. So these are so-called colored fields. The quarks participate in these interactions.
I think that might be a good place to stop, because we're almost out of time now.
Oh, we are all.
We will stop here for now and continue in the next episode. See you then.